So, domain and range, also known as the inputs and outputs of a function. We have an example here that says the cost in dollars of making X pounds of candy is given by the function C of X, which we know X is our inputs and the C's are our outputs. The cost in dollars, so the C is representing the costs of making X pounds of candy, so X is pounds of candy. Might be helpful to write that down for ourselves, is given by this function 10x plus 500. Part A says the fixed cost is determined when 0 pounds of candy are produced. Find the fixed cost for this number of pounds. So the question here tells us that we are producing 0 pounds of candy. That's going to be it's going to give us the, I guess that should be blue because that's talking about inputs. And then that's going to tell us the fixed cost of kind of manufacturing candy, like without manufacturing any.
Where is that at? The workbook?
Yeah.
Which page?
12.
You're not screen sharing.
Oh.
Yeah, that's why.
Wait, why am I not screen sharing?
That's why.
Sorry. Let me fix that. Thanks for saying something. Okay. We are on page 12 of the notes. Let me let you catch up. So that's what I've done so far with this first example.
Domain and range, right?
Yeah, domain and range, page 12, section 1.2. Okay, we're working on the first example here. We're good now? Can I continue? Everyone's caught up. Okay. Thanks for saying something. We are talking about 0 pounds of candy, which is going to be our X variable. So we're actually looking for the cost C when X is 0. So we're going to evaluate C of 0. Remember, evaluate versus solve from last time. When we plug in an input value, we're evaluating this function. So 10 times the X, which is 0 in this case, plus 500. Well, 10 times 0 is 0, so we get 0 plus 500, which gives us 500 as a number. If we're talking about this C being the cost of producing candy, then what do you think the units would be for this C of 0 evaluation? What do you think the fixed cost is going to be? What are the units of cost? Dollars, good. So we're going to write here as our answer, we're going to say fixed cost is $500. I mean, if you just wrote $500, as long as you put dollars on it, I don't really mind if you didn't write the whole sentence. But just make sure you're aware of units when it comes to, this is essentially a word problem talking about real world things. So if it's telling you pounds of candy, that's a units. If it's telling you cost in dollars, that's a units. So make sure your answer has units in it. Okay, and then we can just highlight these as the ones that you will be working on. So put a star next to those or something so that when you go back, you know which ones you're supposed to be working on. So you guys will do B and C when I put you into groups. Are there any questions on that first part? Why we plugged in 0 for X?
Okay. Hold on.
Go for it.
Let me look at it.
Okay.
You can keep lecturing.
Okay,
I'm
thanks.
still gonna look at it.
Okay. Uh, um, Inequality interval and set builder notation. Um, if you watched the video, hopefully you got an idea of this. If you didn't, then you're going to need to look at these. You may have seen interval notation before, so this is kind of a review of that. Important things I want to highlight are if you have a point that's not included, an endpoint that's not included in your interval, then we use parenthesis to signify that endpoint. So if you have like the interval from A to B, but A and B are not included in your interval, then we use parentheses for our interval notation. Whereas if you want the endpoints included, for example, down here, this one has the A and the B filled in, and we want everything in between A and B as well, then we use brackets to signify that we're including those endpoints in our interval. So when you see something like this, and we're talking about interval notation, this means everything from A to B. So if we saw like, I don't know, 2 to 7 with something like this in interval notation, we would do a number line. We would put 2 on the number line. We put 7 on the number line. You can put all the numbers in between as well if you want. You don't really have to get the point across. But the parentheses next to the 2 tells me that I don't want to include the 2, so I want an open circle at 2, saying we're punching a hole at 2, and then the bracket around the 7 tells me that we want to include 7, so we're going to put a closed circle at 7, saying we are going to include that number 7, and then we would want everything in between. So we shade everything in between. That's what this interval represents on a number line, right? It's every number between 2 and 7, not including 2, but including 7. And then infinity always has a parenthesis because this, where's my infinity one? So if you have an interval that goes on forever in one direction, you're going to use infinity to signify that we do go on forever that way. And infinity always has a parenthesis because infinity is kind of an open-ended concept where there is no like reaching, that you don't reach an actual point called infinity. You just include all points forever. So we use a parenthesis there because there is no hard stopping point, right? The brackets are hard stopping points. Infinity goes on forever, so we use parenthesis for that. You guys can do that example, so we'll highlight that 1.2.2. You will do that in your groups. Next thing is finding the domain of a function defined by an equation. So instead of doing an example on this one, I'm going to give you general, I'm going to recap the general domain restrictions that you will run into in life. We'll do it over here. There's essentially there are 2 restrictions. Well, we're only going to see 2 restrictions for domain, so I'll go over those. One is rational functions. Meaning fractions. But not like fractions like 2/5 or 1/2. Fractions like this example down here where you have a function that has variables in the numerator denominator, okay? More specifically, variables in the denominator. For rational functions, we're just going to need the denominator not equal to 0. That's your setup for finding the domain of a rational function. So you take whatever's in the denominator, which is the bottom part of your fraction, and you just make sure that it's not equal to 0. In order to make sure it's not equal to 0, you just need to figure out what input values would make it 0, and you just don't include those in your domain. So domain is essentially everything that can be plugged in as input in kind of general terms. It's every number that can be plugged in as an input. So this when you have a fraction like this, this denominator because we know that we can't divide by 0, and that breaks the rules of life and math, we just have to make sure that this denominator never becomes 0. So that's what this whole thing is. You're going to take your denominator, you're going to make sure it's not equal to 0. So figure out what would make the denominator 0 and just disclude those from your domain. Number 2 type of restriction you're going to run into is square roots. And for a square root function, and that's example C, I'm guessing, down there. If you look at part C of this example, that will be the one to look at for that. You're going to want to just make sure that the inside of the square root is whatever's inside your square root needs to be greater than or equal to 0, because we can't have negative values inside of a square root. These things I'm giving you, this denominator does not equal 0 and inside of the square root greater than or equal to 0, are essentially how you set up how to find domain of these functions. If there is no square root or fractions, like in this first example here, then your domain is simply everything. So we can write all real numbers for the domain, or if you want to write it in interval notation, we're going to say negative infinity to positive infinity. But essentially, we can plug in anything we want in for x here. So you're going to do these examples, except I'm going to change the question slightly, and you don't need to find the range. So let's get rid of the range part of that. We'll just find the domain for now. We'll talk about range in a second when we look at the graph of some functions. So make sure you change that so you're not confused about finding the range there. Okay, so moving on, using graphs, how do we find domain range? So we talked about how to find domain of an equation. We can talk about finding domain range from a graph, and this is a great illustration for what we mean by domain and range on a graph. Domain is essentially going to be all possible x values, and range is going to be all possible y values. When we say find domain and range of a graph, we're talking about the domain and range of this blue curve here, okay? So we look at the blue curve and we look at all possible x values that are on the blue curve. So if I picked a random point on here on the blue curve, or let me pick something nicer, I guess. If I pick this point here, that has an x value of -4, right? So -4 is a possible x value on this curve. If I pick a point over here, +1 is a possible x value, but so is +2, and everything in between +1 and +2, right? So if I were to look at to find the leftmost point on this graph, it would be this one here, because there's a solid point here, and that's -5, right? So -5 is essentially the smallest x value on this blue curve, right? Because every point on this blue curve has an x and y value attached to it. This is -5, 5. I don't know, this is 2, -1, and this is -1, -2, and so on. So all of these are points on the graph. We want to signify every single one of these points with our domain and range. So domain is going to be all of the x values. So all of the x values, meaning if I go from left to right, which x values does this blue curve span? So if I scan from left to right, if I go this way, I'm hitting points. it looks like we go from -5 as our smallest. So we'll write out this one: domain and range. It looks like the domain starts at -5, and because we're using interval notation, we want to include that -5. We'll use a bracket there. 2. What does it look like the biggest x value is going to be on this?
5.
5. Does it look like it'll ever reach 5 though?
Maybe.
I don't think so. I think this is to better understand this, there would need to be a kind of a vertical asymptote signified here. It does look like it's getting vertical, so I'm going to assume there's a vertical asymptote there. And we're going to well, no, it doesn't get past that vertical dashed line that I drew, so it doesn't get past 5. So we're going to say it goes from -5 to 5 with a parenthesis because it never actually reaches 5. This line goes down forever and keeps getting closer and closer to this vertical asymptote at 5, but never actually reaches it, right? So we can get as close to 5 as we want. We can go to 4.9999999, and there will be a point there, but not at 5.
So when there's a parentheses, does that mean it can go on forever?
The parenthesis just means you don't, the x values don't ever reach 5. Like on a number line, it would be 5 would be here. We would have an open circle, and the points would get really, really close to that, but it would never reach that 5. So not necessarily go on forever. The go on forever going downwards is going to be more of a property of the range. So the range, if I wanted to write the range, what is the smallest y value that's on the blue curve?
-1.
No, there's points down here that are smaller than that. Like this is,
Oh.
what is it like this? Like if I go down here, this is like 4.5 comma -7, for example, right? If this line keeps going down forever, then my y values will keep going down forever, right? So there is no end to the y values here. There's no cutoff like this to stop the y values. So actually the smallest y value is going to be, well, not a value, but it's going to be -infinity, correct? Because there's a down arrow and the graph is going down forever. What's the largest y value on our graph?
5.
Good. So we look at the highest point on the graph, and that is the 5 for the y value. And this is a closed point, which means we do actually reach this 5 on the y-axis. So that will be a bracket for the range.
So a bracket reaches the number?
Yes, and the parentheses
write that
doesn't
down.
reach the number, yes.
People are writing an E.
Okay, and then let's highlight this one. You guys will be working on 1.2.4 when you get to your groups.
So, what does parentheses? Does it mean like it goes on forever?
No, parentheses, it doesn't reach.
Alright.
And brackets reaches. Okay, moving on, graphing piecewise defined functions. Piecewise defined functions are functions like this, where you have multiple pieces depending on which part of the graph you're looking at. Essentially, this part of the piecewise function is the how the domain is split. That tells you where each part of the graph is located. If we were to try to plug in numbers into this piecewise function, so this is, let's read through this. A cell phone company uses the function below to determine the cost C in dollars for G gigabytes of data transfer. So we have our inputs and outputs. Our inputs are G gigabytes of data transfer, and our outputs are cost C in dollars. And so there's a different rate for 0 to 2 gigabytes, which is just 25 flat, versus more than 2 gigabytes of data used, where they start charging based on this function here. Okay, so that's how you would interpret this function. Find the cost of using 1.5 gigabytes. So this 1.5 gigabytes is an input, right? So we need to figure out which one of these two pieces we're going to plug that into, because they're both pieces of the same function. 1.5 gigabytes fits into only one of these two areas, right? Which of these two, is it the first one or the second one, the 1.5 falls into?
The first one.
First one, thank you. So then that means we're going to plug in 1.5 into this first function, or into the first piece of the piecewise function. So
because it has a 0?
because it's between 0 and 2. This is saying between 0 and 2.
Okay.
C of, so if we're solving this, we would say C of 1.5. If I want to plug in 1.5 into this function, we would plug it into the first piece of the function. How do I plug in 1.5 into this first piece? Where does it plug in?
Where the G is at?
Where is the G?
After the equals? After the equals?
In this function, where's the G?
Oh,
Is it automatically
was-
25?
it's,
Yeah, there's no G in that function, so there's nowhere to plug in. We just get automatic 25.
Oh.
So this C of G is essentially both of these functions. But it's the first function for this range and the second function for the second range. So because 1.5 falls into the 0 to 2 range, we're going to plug into the first function here, but there's no G's to plug into, so we just get 25 for that. So the answer for the first part is $25. And the second part of the question says, find the cost of using 4 gigabytes of data. So we want to find C of 4. And I know that 4 is greater than 2, so it's going to fall into the second category of this piecewise function. So we're going to plug in 4 into the second piece. So that second piece is 25 plus 10 times G minus 2. No, sorry, not G, right? We're replacing G with 4 in this case. So we evaluate 25 plus 10 times 2, 25 plus 20, which is 45. So the answer here is $45. Questions?
let me look at it real quick. Okay, I think I get this one too.
Any other questions?
I may need a little help on the graph one.
Yeah, we'll talk about the graphs right now. So how does this idea work in graphing? There's a great example here that shows how to kind of build this final graph at the bottom here that looks like it's a broken graph, right? It has two pieces to it. How to build that piece by piece. So if we look at our function here, remember it has two pieces, right? So we're going to graph those two pieces in their respective ranges, or sorry, not range. I don't want to call it range. In their respective domain regions. So between 0 and 2 on the g-axis, so from here to here, we're going to want to graph this function, the f of g equals 25 function. And that's just a flat horizontal line. And since we're graphing it from 0 to 2, we see a horizontal line from 0 to 2. Does everyone see how that was graphed? So from 0 to 2 on the g-axis, we're going to graph the flat line 25 because that's what this function's graph would look like. If I didn't have this restriction from 0 to 2, this f of g equals 25 graph just goes on forever as a horizontal line at 25, right? So this restriction here, 0 to 2, just cuts that off at the two endpoints, 0 and 2. And these are open circles for a reason. Why are these two open circles? Can anyone tell me why we think those are open circles and not closed, like filled in points?
Because it told us 0 to 2.
Correct, but why is it not a filled in circle? Because 0 to 2 could be a filled in circle as well.
It's not included
Well, how do you know that?
because it's not the greater than sign or like less than sign doesn't have a line under it.
Good. So it's these specific symbols here that are telling us that this inequality is saying 0 is less than g. It's not saying 0 is less than or equal to g, right? There's a difference between those two things. If it was like this, where it's less than or equal to, or 0 is less than or equal to g, less than or equal to 2, this would have these holes filled in. Okay, so this, the interval notation stuff, the inequality stuff, you need to know. This means open circle at 0. Sorry, open circle at 0 is 0 is less than g. Okay, and then the second piece over here on the right side tells us that we're going to graph this function, which there's a few ways of graphing that. That's a line. You can figure out what the slope is. You can just do like a quick GC table to graph this by just plotting a couple of points. This is a linear function, so I know it's going to be a straight line. If we didn't have this restriction here, we would end up with a line that goes like this forever, up and down. But because we have that restriction, we're only interested in the part of it that is from 2 on to the right. Right, because we want all of the g's that are greater than or equal to 2. And in this case, we have the inequality that has the greater than or equal to sign, which means we want a closed circle as our endpoint, and we want all of this that is to the right of this invisible line here. Okay, so this function here with this restriction graphs to this solid point and this line that goes on forever up and to the right. Okay, and then finally, we're going to put these two ideas together because those are the two pieces of our piecewise function, and we're going to end up with a combination of these two graphs. Okay, in general, you don't really need to do it on separate graphs because there should be no the way that piecewise functions are written, this should be a splitting of the domain. There should be no real overlap between the two, except for at endpoints where they could like connect to each other, kind of like how this open circle here and this point here are at the exact same place. So when we put these two graphs on the same graph, we see they kind of join together at this corner here. Okay, this corner is where the open circle was from the first graph, and then the closed circle was from the second graph, so that closed circle fills in that open circle. So we get a continuous with a corner. Yes?
What's the difference between an open and a closed circle again?
It has completely everything to do with these inequalities here. When it's just less than, you're going to have open circles. When it's less than or equal to or greater than or equal to, has the line underneath it, you're going to have a closed circle at that point.
So more than is a arrow?
No, these it has to do with whether it has the equals to sign underneath it. If it doesn't have the equals to, the arrow is just because there is no, this just says g is greater than 2, greater than or equal to 2. What does g greater than or equal to 2 mean? It means, actually we should write that, I guess, to make it more clear. G is greater than or equal to 2 means 2 with a closed bracket to infinity. The infinity is the part that means the arrow.
Hold on, quick.
The infinity is the part that's going to translate to an arrow. So you need to be able to go back and forth between these inequality notations and interval notation. So this one would be from 0 to 2 with parentheses, right? That's that in interval notation. Okay, so just to recap, we graph each one separately in its interval, respectively, and then we put them together into one graph with the same scale and everything. So this was the first piece of the graph, and this was the second piece of the graph. So we put them together, we get one graph for this piecewise function. Okay, you can follow that example to kind of do this example down here, 1.2.6. So you'll be working with this piecewise function here, and it's kind of split into 3 parts again for you. So you can do the first part, graph the first part, graph the second part, and then join them together to give you the whole piecewise function. Like I said, you're not always going to want to do it in 3 steps like this. You probably want to get to a point where you do it in one graph. Just you do the splitting kind of one piece at a time on the same graph, right? And since there is no real overlap, you should be able to do that. Okay, moving on to the absolute value function. Let's talk about this is one of our toolkit functions from the first section. At the end of the first section, there were some functions that we should be aware of. The absolute value function is essentially the V-shaped function that we've seen before. It kind of has this graph that does this V shape, right? We should have that general idea about it. You should kind of have an idea of what it does to numbers, right? Can someone describe to me what the absolute value function does to numbers when you plug into it?
They keep on going.
But what does the absolute value function do to a number when I plug it into it? Like when I plug in 7 into the absolute value function, what happens? What do I get?
Positive.
Turns it positive, yes. So if a number is positive, then what does it do? Because you can't say turns it positive because the positive numbers are already positive, right? So how else can we describe that?
Keeps it positive.
Keeps it positive, meaning it doesn't do anything to it, right? It just gives it back to you the same way, right? If you plug in 7, it just gives you back 7. If you plug in a negative number, what does it do to it?
Turns it positive.
How do you think it can turn it positive? Because it's easy to say turns it positive, but mathematically, how would we show that? How would we actually turn a number positive mathematically? By doing what to it? How would we get rid of that negative?
Multiplying by a negative.
Yeah, multiplying by a negative. Which is how this piecewise function version of the absolute value function operates. Okay, let me read through this in a way that I would read it. This piecewise function, which is the absolute value function, split into 2 parts. The most natural way to split the piecewise function into 2 parts, if you look at the V-shaped graph, where are the 2 pieces splitting? They are splitting at 0, right? So we're going to split our x values at 0, and we specifically want to do something to the negative x values different than what we would do to positive values. So these x is less than 0 is describing all of the negative values that x could be, and the function is doing a -1 times x when it comes to negative x values, which is essentially what you guys said turns them positive, right? So when x is a negative value, we multiply by a negative, which makes them positive when they come out. If x is already 0 or positive, which is the second part, x is greater than or equal to 0, we're not going to do anything to it. We're just going to output x as is, right? So that's how the absolute value function can be split into a piecewise function. It does essentially tell the number from, or tell the distance from 0, but as a function, how it operates is essentially a piecewise function. Just something to keep in mind. I don't know if you've ever talked about an absolute value function being a piecewise function before, but this helps us talk about certain characteristics of the absolute value function, because now we can actually incorporate a mathematical notation for it instead of just the concept of making things positive, right? We've only talked about the absolute value of just making things positive. Now we can actually do mathematical things on it because we know it is a piecewise function. Okay, and then there's an example here that you guys can work on. Again, it's just graphing. I don't know why they put this here after the absolute value function thing. It doesn't have to do with the absolute value function. This is just a piecewise function with 3 pieces, and you're only given one graph. So you're going to have to graph all 3 pieces on this same graph. Something that helps me graph these is to start with the splitting, how the domain was split. Okay, start with that. Give yourself some guidelines on where each piece of the graph is going to be. So I'll kind of get this started for you, I guess. What are these splittings? Let's talk about some of these intervals. This middle interval here is the most fun one because it has both endpoints, so it's going to be kind of kept on both sides. This middle interval here is from 1 to 2 with an open parenthesis at 1 and a closed capped bracket at 2 because of the inequality symbols that we see here, right? So we're going to go from 1 to 2. So what I would do on the graph is I would say from 1 to 2, I'm going to put these vertical dashed lines that I will probably get rid of later because they're not actually part of the graph, but it gives me a window to look at when it comes to graphing that middle piece. So we're going to graph a piece of the function, this piece specifically, within this window here, right? Just looking at this window. The other windows are essentially the other 2 sides of this graph, right? So once I have this window mapped out in here, the top one is saying x is less than or equal to 1. That's just going to be to the left of this window that we've drawn. And x is greater than 2 is going to be to the right of this window drawn. Okay, so the 3 pieces, the first piece will be in this area somewhere. The second piece will be in this middle area somewhere where we kept the window. And the last piece here is going to be somewhere on this side of the window that we drew. Okay, and then once I've drawn those, I would get rid of these because they're not part of the graph, right? It's just going to be some curve on this side, and then some other curve between this window, and then another thing over here. Okay, it's going to look like it has 3 pieces. So when you graph that, keep that in mind. I would start with figuring out where you're going to graph each piece. Okay, are there any questions on 1.2 before I jump into 1.3?
I honestly don't get it.
I will come when you start working on the examples.
Yeah.
If you can't figure it out, then you can call me to your group and I'll
Okay,
try to help you with the examples, okay? Any other questions on 1.2? Okay. 1.3 is more about the absolute value function, and I see what you meant by tells the distance from 0, because that's how we're going to talk about the absolute value function here. The absolute value function essentially tells you your distance from 0. So when we do absolute value of -5, we're asking the question, how far is -5 from 0 on the number line? So if I put -5 here on the number line, and I put 0 on my number line, how far is that? That's distance. Does it say that anywhere in here? The reason why we define it as distance is because distance is defined to always be positive. Right, distance is a positive measurement. When you use a tape measure or a ruler or something, you're never going to get a negative number from a ruler, right? So When we talk about distance, we're talking about the positive unit distance from one point to another. So the absolute value of a number is its distance from 0 on the number line. We write it as vertical bars around a number, and it is always a positive value for all numbers. What is this example? Use an absolute value inequality to describe all values x within or including a distance of 4 from the number 5. So this is an interesting way to incorporate absolute values into kind of an English sentence. So let's try to figure out what goes where in this sentence. We want to describe all values x within a distance of 4 from the number 5. So the distance is going to be 4. So distance equals 4 is what we want to work with here. No, erase that. Hold on one second. Yeah, sorry, I was on the right track. I just second guessed myself. Let's rewrite that. Distance is going to be 4. What do we want to be 4? We want all of the numbers, all of the values x that are a distance of 4 from the number 5. So in this example up here, when we do absolute value of 5 or negative 5 or whatever, our baseline point is 0, right? We're doing a distance from 0. So if we wanted our distance to be measured from the number 5, we kind of have to shift our number line so that it's centered at 5. So what we're going to do is we're going to say we're either going to do 5 minus x, or we're going to do x minus 5. I like 5 minus x better because there's a positive 5 in this expression here, where the center of our number line is going to be. So we want the distance from 5 to be 4. So this part here, let me move this a little bit. This part here is defining distance, or let's not say distance. This part is centering number line at 5. Right, so we just throw the 5 in there, and then we subtract x, which centers our number line at 5. We could also do x minus 5 here, because the absolute value function you can flip that around and it doesn't matter. I like this notation better because you have a positive 5 in there, which is centering your number line at 5. So when you want to find, when you want to describe all values x within a distance of 4 from the number 5, you want your distance to equal 4. So this absolute value is going to define that distance, and we want that distance to equal 4, right? And we just need to center the number line at 5. So we do 5 minus x in this parenthesis, or in the absolute value. Okay, and that's it. This is our actual answer here, because we just wanted to describe using an absolute value. We needed an inequality. Why do we need an inequality? Because if I set this equal to 4, it would find the exact points that are 4 units away from 5. Instead, we want within 4 units. So we want to make this an inequality of less than or equal to 4. So on a number line, let me show you what this looks like. We center our number line at 5, and then we go left and right x units. That's what this absolute value with the minus x is going to do inside. We're going to go left and right until we reach a distance of 4, and we're going to include every point in that movement. So we're going to start at 5, and then we're going to go 1, 2, 3, 4 this way, 1, 2, 3, 4 this way. And so we're going to count all the way here, and we're going to include all of these points all the way to, what is this, 1? 1, and then 9 is where we get to on the high end. So we get all of these points between 1 and 9, as described by this absolute value inequality. So this 5 minus x centers the number line at 5, and then we do the inequality because we wanted within 4, within a distance of 4, and not exactly 4 away. If I left it as an equality, we would just get this point and this point, the one at 1 and the one at 9. We would only get those points. Okay, and then you guys will do this example. You're kind of doing the same thing with a different wording. Solving an absolute value equation. So when you're solving absolute value equations, you're essentially going to need to split the expression into 2 parts. The 2 parts we're going to split into are based on if the expression inside of the absolute value was positive versus negative. Because remember, that's how we split our absolute value function into a piecewise function, right? On whether or not the inside was positive or negative. So we're going to do the same thing here. If the x minus 5 that's in here, so I'm gonna do this first example for you. If this x minus 5 that's in here, inside the absolute value, if that's already a positive expression, then what would the absolute value do to it? What would the absolute value lines do to a positive? It would keep it positive, which means it would do nothing, right? So the first piece that we're going to write is not doing anything to that x minus 5 and just rewriting it. Or what if the x minus 5 was negative? What would the absolute value function do to it?
It would still be positive.
How does it make it positive?
Because, it probably just turns it negative.
No, it's already negative.
Oh.
How does it make it positive? How does the absolute value function make it?
It would just, keep on going up to, the positive line.
No, how did we define it here? If x was negative, what did we do to the x here in the piecewise function to make it positive?
Multiply by a negative.
Multiply by a negative. So we're going to take whatever's inside there, the x minus 5, and we're assuming it's negative in this case. So we're going to multiply by a negative 1 to make it positive. And then we'll still be equal to 4. And now we just have 2 equations to solve. And we should be able to solve these. We just use our traditional methods of solving. We'll add 5 to both sides. X is equal to 9 on this side. Or we can, we can distribute this negative if you want. Or we can just divide both sides by -1 to get rid of it. X minus 5 will equal -4 in this case. And then once we add 5 to both sides, we'll have x equals +1. So we have this answer here. So 2 pieces, one where you don't do anything and you just take the absolute values off of the equation, and then the other one we multiply whatever was inside the absolute value by a negative. Right, and then you solve each one separately, and both of these values, if you were to plug them back into this equation in your problem, should give you a 4 equals 4. Right, so there's an easy way to check these. If I plug in 9 into here, 9 minus 5 is 4. Absolute value of 4 is 4, which is equal to 4. If I plug in 1 into this x here, 1 minus 5 is -4. Absolute value of -4 is +4 again. So both of these values should work in that situation. So let's highlight this part B that you guys will be working on. And then move on. Solve an absolute value inequality. Okay, so we do the same thing when we're solving absolute value inequalities. The only part that changes is when you're actually solving the 2 pieces, right? There might be some things to worry about, or you need to know how to solve equations like this involving inequalities when you're doing these problems. So again, I'll do the first one and you guys can work on the second one. So if I take this, again, we're going to take whatever's inside the absolute value, and we're going to split into 2 pieces here. The first piece, we're not going to do anything to it because we're going to assume it's positive. So we're going to say x minus 5 is less than or equal to 4. All right, we're not going to multiply by a -1 on this one. We're going to say or, and then in the other one, we are going to multiply by a -1 on the outside with the less than or equal to 4. Oh, this is wrong. No, it's not wrong. But why would they do that? This is pretty annoying. Okay, I'll have to talk to the coordinator about this. We're gonna add some corrections in here. Let's add some notes in here. This up here is telling you all the different ways that you could have an absolute value inequality. You can have an absolute value less than a number. You can have an absolute value less than or equal to a number. You can have an absolute value greater than a number or greater than or equal to a number. Because there's 2 different versions of each direction of inequality, you get 4 different ways that you could have an equation here. We're going to group some of these together. So these 2 with the less than and the less than or equal to, we're gonna say that these will turn into and when you split into two cases, whereas these two, the greater than or equal to and the greater than inequalities, will split into or inequalities once we split into two cases. And there's a difference between and or inequalities that I'll talk about in a second. But that kind of throws a wrench into this example that was done in here. So let's change this to an and, because it should be and, not or, in this example. And the answer should be and as well. Okay, I think that's okay for now. We'll talk about what and or are in a second here. So our example here, which category does that fall into? The one that we're working on.
And
It does. Good. So we're going to write and in between these, not or. Because in the end, we're gonna actually just do the intersection of those two answers. Okay, now we can get into solving these inequalities. So how do we solve inequalities? Well, we solve them the same way we solve equalities. What do we have to be careful about inequalities? There was something special about inequalities when we're doing operations to them.
we minus 5 each side.
We're going to add 5 to each side
Oh,
because there's already a minus 5, right? So x is less than or equal to 9 is what we get there.
yeah.
Okay, what do we do last time on this one? We divided by a negative 1.
Yeah, we divide by 1.
Good, let's divide by a negative 1 here. X minus 5 will be, what do we have to do when we divide by a negative 1?
Flip the equality sign.
Flip the inequality sign, yes. So we need to flip it to greater than or equal to negative 4. So whenever you multiply or divide by a negative value, you flip the inequality. And then we can go back to our regular operations, add 5 to both sides. X is greater than or equal to 1. And our answer here is going to be an and answer. Whenever you have an and answer for an inequality with two pieces joined with an and, you can put them together. So we'll start with the small number, which is 1, and we'll say less than or equal to x, less than or equal to 9. So we can put them together into a single kind of double inequality where we have x in the middle, because this is saying that x is numbers that are smaller than 9 and x is numbers that are bigger than 1. So this is saying the same thing, right? X is all numbers between 1 and 9. So when we put these two together, this should make sense on how we put that together.